This lesson is supplemental problem 3.3. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems on page 4. Integrated circuits are biased with current sources instead of voltage sources. Even though we hook up a voltage to run an IC, we'll see that it creates a reference current in the chip, and that reference current is moved around in what's called a current mirror. In other words, a mirror image of it is created. This particular current mirror was part of a Motorola wide bandwidth video amplifier, whose part number was MC1553. If you make all the transistors on the same piece of silicon at the same time, then you can assume that they're identical. In other words, they have the same Ebers-Moll parameters. I'd like to solve for the current I sub C1, I sub C2, and then the base emitter voltage. You can see here the base emitter of transistor 2 is the same as 1 because we're hardwiring those together. Let's assume that the transistors are active because I've got 3 volts across here. Let's assume that beta F is 100, eta F is 1, and that I sub ES is 10 femtoamps. These are typical numbers for an integrated circuit. Let's first solve for the current in the emitter of transistor 1. Now because it's in the active region, we could approximate it as this part of the Ebers-Moll equation, where I've got I sub ES times e to the VBE of transistor 1 over eta F V sub T. Now since the base emitter of transistor 1 is the same as transistor 2, we're always going to call it VBE, then this says that the emitter current for transistor 1 and 2 are the same value. Since the collector current of transistor 1 and 2 is related to the emitter current by a beta F relationship because they're in the active region, then they're also equal, and likewise for the I sub B's for transistor 1 and 2. The current coming in here is some reference current, and we'll actually solve for this in later chapters, and that current has to equal the base current of 1 plus the base current of 2 and the collector current of 1. So that's the expression over here. But the base current of 2 is the same as 1. We've got twice that value. And then the base current is related to the collector current divided by beta F. And I could solve for the collector current. The 780 microamps, I'll pull out the collector current here, which is going to give me 1 plus 2 over beta F, and then divide that into here. And then I can plug in the fact that beta F is 100, and that the reference current is 780 microamps. That gives me 764.7. You can see this number is pretty close to this one, and the bigger value you have of beta F, the closer these two will be. We're creating a reference current, we're creating a mirror image of it. The emitter current of transistor 2 is related to beta F plus 1 over beta F. It's a little bit bigger than the collector current. This would be 101 over 100. And that's equal to 772.35 microamps. The base emitter voltage for transistors 1 and 2 is eta F E sub T times the natural log of I sub E over I sub E sub S. We have an eta F of 1 of E sub T roughly of 26 millivolts at room temperature, an emitter current of 772.35 microamps, and an I sub ES of 10 femtoamps. That turns out to be 651.8 millivolts. And we'll see for integrated circuits that the base emitter voltages are more in the neighborhood of 0.6 volts than 0.7 because the transistors are a lot smaller. And this is supplemental problem 3.3.